Okay, now let me start defining some of the terminology that we'll use for the rest of the semester with graphs. We usually denote graph with a capital G, and really all a graph is a set of vertices that we usually denote with a capital V, and a set of edges that we'll usually denote with a capital E. So graph, standard symbol for representing a graph. V is the standard symbol for representing the set of vertices. A lot of times you'll also hear me call those nodes, and I think I've already done that in the previous video. I'll try to stick to vertex and vertices, but I'll probably use those interchangeably. Just it's a hard habit to break. Also, we will almost always denote the number of vertices as n. So, for example, when we're sorting n numbers, we use n to represent sort of the count of numbers that we're sorting. Here we're going to say that the size of the graph n is equal to the number of vertices. And this notation here is basically saying what's the cardinality of that set of vertices. So how many elements are in that set. E, again, standard set for edges, and we'll usually denote that as m. The number of edges is m. Each edge is going to contain a pointer to two vertices. So an edge is really nothing other than two vertices. It looks something like that. Parenthesis v1, comma, v2. And the order of the vertices may or may not matter. So let me expand on that just here briefly. We can have two types of graphs, or rather we can have a lot of different types of graphs, but one way to divide graphs is to say that we have directed graphs and we have undirected graphs. So here if I have an undirected graph, my notation here for the edge would be an AB edge, or I could also say a BA. It doesn't matter for an undirected graph. The edge has no direction to it. For a directed graph, I'm only ever going to denote that with CD, and a lot of times you'll hear this called the tail, and this the head, because it's at the head of the arrow and the tail of the arrow here. The only really important thing to remember is that this edge goes from C to D. Alright, well let's start with sort of the most fundamental algorithm we can have for a graph, which is called graph search. Sometimes it's called findability, sometimes it's called connectivity. And what we're trying to do here is find everything that's findable. And the term here, findable, just means we have a path from a start node to this particular node that we were able to find. We also want to do so efficiently. There's no reason for us to explore anything twice. So if you've already found a vertex, there's no reason to find it again. It turns out that this graph search can be done in linear time. And we'll call that big O of n, because it depends on the number of vertices. And again, I think I've mentioned this previously in this semester, which is, a lot of these linear types of algorithms you can think of just as doing as a free thing as part of the pre-processing step. If it takes big O of nm just to read in a graph, you have to read in all vertices and all edges, then, doing another graph search here is not going to take up much more time than that. You might double the total running time that you're working on, but you're not going to have sort of something that's at a different complexity level. Alright, so here's an example of findability. The first question I'll ask here is, what's findable from this start vertex S? Well, this is an entire graph, so all of these vertices are in the graph. And if we follow our edges, we can get to 1, we can get to 2, we can get to 3. Those are the only vertices that are findable from S, so I'll highlight those in yellow. Now let's compare that to a directed graph. And again, what is findable from S? Well, now we can't get to 2 anymore. There's no edge going that direction. So we can't get to 2, we can't get to 4, and we can't get to 5. Alright, well let's look at a little bit more complicated question. So what is findable in this graph? Well, this first one was a trick question. I need to give you more information. It depends on where you start. If I start up here, that's going to give me different things that are findable versus if I start down here. If you assume that I was starting at S, that's a pretty good assumption. I'll almost always denote the start vertex as S. But if I'm asking you what's findable, it's perfectly reasonable to start by just asking me findable from where. Okay, so what's findable from S here? Well, it's everything to which we have a path to it. So we can just sort of go over each of these and we can say, A, do I have a path from S to A? Well, yes, I have a direct edge there. Do I have a path from S to B? Yeah, direct edge. Do I have a path from S to C? yeah, I can go up to A and then over to C, and you'll see that basically each time around, if you're thinking about having an algorithm to actually solve this, you'll just look at, okay, well, what have I found so far, and what are the outgoing edges? So we'll start here with S. What are its outgoing edges? Maybe I find A, and now the outgoing edges are the AC edge and the SB edge. And just as a reminder, since this is an undirected graph, I could also put this as the BS edge and the CA edge. And then we'll continue on until there are no more outgoing edges. So what's findable from S? It's A, B, C, D, and E. Okay, I'm going to end this video here, and here's where you should try to work out exercise question 1 before you move on to the next video, before you move on to the next slides. It's good to think about this algorithm before it's shown. That'll make it stick a lot better.